Alright, welcome back. In this video, we're going to go over Sn2 reactions. Here's what we're going to do for this video. I'm going to take it really slow. The reason is because this video might be the most important video of your lifetime. Because this will make or break your organic chemistry experience, I should say. That's a little more extreme. But everything going on forward is basically Sn2 reactions or E2 reactions. So here's what we're going to do. First, I'm going to talk about alkyl halides and what they are. Then I'm going to explain why we're learning this and how this relates to Sn2 reactions and Sn1 reactions. Then we're going to compare them. What are Sn1 and Sn2 reactions? Then I'm going to tell you a trick to figuring out when to use Sn2 or Sn1. And then we're going to go over stereospecificity. And we'll do some practice problems with Sn2. There's going to be no Sn1 practice problems because I really wanted to focus just on Sn2. Because in organic chemistry exams and midterms, majority of the questions are going to be Sn2 and E2 reactions. Not too many Sn1 and E1. Not saying that there won't be. There probably will be Sn1 and E1, but I will make practice problems a little bit later in the week. But since Sn2 is a really big component to your exam and future going on, I really just want to focus on that. And then we're going to do a challenge problem. This challenge problem looks very complicated, but I can tell you with confidence that after after watching this video, you'll be able to do this with no problem. All right, let's begin. What are alkyl halides? Well, alkyl halides are basically halogens that are attached to carbon atoms. So alkyl basically means carbon, and halide sounds like halogen. So it's basically carbons bonded with halogens. And that's exactly what it is. So alkyl halides undergo two main types of reactions. They undergo substitution reactions and elimination reactions. Substitution can be further divided into Sn1 and Sn2 reactions, and elimination reactions can be further divided into E1 and E2 reactions. Substitution reactions is where the halogen, or rather the alkyl halide as a whole, gets replaced by a nucleophile. So in other words, the alkyl halide as part of the main compound gets substituted with the nucleophile, as you can see here. The halogen has now been replaced by the nucleophile in the original molecule. And then that halogen is now set free. And in an elimination reaction, we basically use a base to eliminate the alkyl halide and replace it with a double bond instead. And then the halogen is set free. Why do we use elimination reactions? Well, in organic chemistry, say if your starting compound does not have a double bond, but the product that you want to make does have a double bond. This is why we use elimination reactions to make double bonds. Substitution reactions do not make double bonds. All right. Now, substitution and elimination reactions will only happen if there's a strong leaving group. An example of strong leaving groups will be chloride, bromide, and iodine. Notice that fluorine is not there. The reason fluorine is not there is because it is not a strong leaving group. What makes a strong leaving group is if it's a weak base. Chlorine, bromine, and iodine are weak bases. That's why they are great leaving groups. Fluorine is not one of those. So, that is why these can be used in substitution and elimination reactions. So why are we learning this? Well, alkyl halides basically serve as building blocks for more complex materials. So say if I wanted to make something like this, right? Well, it actually starts with alkyl halides. It could start with alkyl halides. So that is why we use this. All right, this is why we use alkyl halides, because we can convert an alkyl halide to an alcohol, for example, using sodium hydroxide. Or we can use an alkyl halide and turn it into an alkene using tert butoxide. Or rather, potassium tert butoxide, I should say. That's why we learned this. Now, what is concerted versus stepwise mechanism? In other words, what are Sn2 and Sn1 reactions? So let me give you an example. Say you go to a house party. You get invited to a house party. This house party you go to is jammed packed, like it's completely full out to the door. There is somebody standing in the doorway. So you're not inside the house yet. You just arrived and you notice it's super full. There is somebody standing in the doorway. There's a really skinny dude standing in the doorway. And what you basically do is you decide to be a dick and basically grab him and push him out of the way and take his spot inside the house. Immediately push him away and take a spot. This is what we would call an Sn2 reaction. This is when everything in the beaker reacts immediately. So if I were to throw a bunch of stuff in the beaker, right, say our compound and our nucleophile, they would all react immediately, meaning the nucleophile would attack and the leaving group would leave all at once, all at one time. Okay? This is what we call a concerted mechanism, or Sn2. Sn2 stands for substitution nucleophilic bimolecular. Basically, there are two things happening all at once. Okay? A stepwise function or stepwise mechanism is also called an Sn1. So for example, say that we're at the same house party and we're outside again. But at the doorway is a really buff dude, like a really strong looking dude. Like, hey girls, you know, I go to the gym, right? Like I'm a pretty strong guy, but I'm not that strong. All right, like, yeah. So I don't have the ability to push this guy out of the way. So what do I do? Well, here's what I do, is I wait until the dude leaves. Then there's an open spot available. I see that open spot, then I make my way to that open spot. Okay? So we do it in steps, essentially. So first, the leaving group leaves, right? Basically, that big buff guy leaves. I see the open spot available in the form of a carbocation, and me, being the nucleophile, will take its spot in the molecule. Okay? That is what an Sn1 reaction is. It happens in multiple steps. Why does this happen? The reason this happens is because if the original molecule with the leaving group is very bulky, for example, let's say that it's very busy, for example. There's no room for the nucleophile to come in, right? There's no room for it to come in immediately. It has to wait until something leaves first, and then the nucleophile can come in, okay? And this will make a lot more sense when I talk about this shortcut right here. But that's basically the gist of it. A concerted mechanism, or Sn2, happens when it's not too busy. There's space for the nucleophile to come in and the leaving group to leave all at the same time. There's space for it to happen, so it happens. There's also something called energy barriers, right? We throw compounds in the beaker. There are activation barriers that we have to go over. If there's a high activation barrier, sometimes not all of it can happen at once. Sometimes it has to take time. And that's when an Sn1 reaction would happen, if there's a high energy barriers. Now here's a shortcut. Anytime you see a carbocation like this, always think of Sn1, okay? In Sn2, there never is a carbocation intermediate. So in Sn1, we have a loss of a leaving group, always followed by a carbocation intermediate. And then the nucleophile will attack that carbocation intermediate to get the final molecule. All right? So when do we use Sn2 and Sn1? Well, when our alkyl halide, so this is an alkyl halide, right? These are alkyl halides. Well, when it's a methyl alkyl halide, for example, this is a carbon right here. So this is the alpha carbon, right? So the carbon that's right next to the halogen, right, that is directly adjacent to the halogen, this is the halogen. The one that's directly adjacent to the halogen is the alpha carbon, okay? So whatever is bonded to the alpha carbon is what we're looking at. So say if there's just a hydrogen bonded to that alpha carbon, we call that a methyl, right? This is okay for Sn2. So Sn2 will only happen when this is the circumstance here. Because it's not bulky at all. There's enough space for the nucleophile to come in and the leaving group to leave all at once. It's plenty enough space. It won't take up too much energy. Same for a primary alkyl halide. So if you see this with one R group attached, remember R can be any molecule at all, any atom that's not a hydrogen. So this could be another carbon, it could be an oxygen, it could be a nitrogen, it could be whatever. This could be 50 atoms long, and it could just be a bunch of carbons, no matter what it is. It's how many branches are coming off of the main carbon here. So we only see one branch coming off the main carbon. So this is the primary or first degree alkyl halide. And this is also okay for Sn2. It's not too bulky. So this can happen all in one process. There will be no carbocation intermediate if you were to do an Sn2 reaction. If you were to do a substitution reaction, no carbocation intermediate. Then we have a secondary alkyl halide. This is when we have two R groups attached to the alpha carbon. It could be either Sn1 or Sn2, but it will depend on the strength of a nucleophile, the solvent, and leaving group. I spelled leaving. There we go. This is a little bit more advanced, so we'll get onto that in a different video. But just know that it depends on the strength of the nucleophile. And I described the strength of a nucleophile in my electrophile versus nucleophile video. Basically, if the nucleophile has a negative charge on it, it's strong. And if it's strong, then it'll do it in Sn2 reaction. If it's not too strong, then it'll do an Sn1 reaction. Now we have tertiary or third degree alkyl halides. This is when we have three R groups attached to it, to the carbon plus that halogen. Notice it is super bulky, right? There's a lot of hindrance here because it's a very large molecule. There's not too much space. This is like the example I gave with that big buff guy, right? We need something to leave first, then the nucleophile will come in and take its space, right? So we have to do this in steps. So this is when we would get a carbocation. So first the chlorine would leave, and then we get a carbocation, and then the nucleophile will come in and attack and take the place of the halogen. So whenever you have a tertiary, then we do Sn1 only. No Sn2 allowed. Never, ever, ever. This is the shortcut right here. So the less complicated the molecule is, that means we're going to do Sn2. The more complicated the molecule is, the bigger it is with regards to the alpha carbon, nothing else, right? I could make this molecule 50 carbons long, but as long as the alpha carbon only has one substituent, right, then there would be Sn2, but if it had 3, it would be Sn1. Hopefully this makes sense. All right, let's talk about stereospecificity. If the alpha carbon is chiral, that means that the R and S configuration switch. So remember, whenever there's an alpha carbon that is chiral, we must designate it by default either R or S. And I also made a video on R and S configurations, so please look at that if you get a chance. So, for example, what would happen? So if you have an R configuration right here, then we have a nucleophile that would attack, right? And then what we're left with is an S configuration now. So everything flip-flops. So we basically get a mirror image. Okay, so now the methyl group that was going left, pointing left, now points right. And then as well as the hydrogen here. Now the shortcut to this is just to change the wedges and dashes to the opposite. So this is a wedge, this would be a dash, and this is a dash, this would be a wedge. That's the shortcut. Okay, I didn't draw it here, but that's the other version of doing it. That's the easier way. And I'm going to show you an example when you do the practice problems. So once again, any time that the alpha carbon is chiral, you must switch all the dashes and wedges to the opposite. You must do this for all Sn2 reactions if the alpha carbon is chiral. So anytime you see a wedge or a dash, immediately you know the carbon is chiral and that you must switch it. If you do not switch it, you will get the problem wrong on an exam. And I know this because I've seen so many people get this wrong. Because they just do the mechanism like normal, right? And they think it's all good. But you must switch it. Your professor may explain something called a backside attack. All Sn2 reactions are backside attacks. In other words, what is it? Well, this is just going over the mechanism, how it works. But when a nucleophile, for example here, attacks, right, this atom right here, this compound, the leaving group here is surrounded by electrons, right? So whether it's a bromine or a chlorine or an iodine, it's surrounded by electrons. The electrons create like an invisible force field. Okay, so imagine it's shielding this halogen here. So what would happen is the nucleophile would actually get deflected, right? It gets deflected by the electrons and bounces off. So what happens is the nucleophile actually goes through the back end of the molecule, like this, right? And then it would kick off the halogen. Because the nucleophile needs to enter this molecule, but the only way it's able to enter is the back side of the molecule. Because the halogen is surrounded by an invisible force field of electrons. These electrons are powerful. It's basically repelling the nucleophile away. It's basically telling the nucleophile, hey, get out of here. I don't want you here. So the nucleophile basically says, hey, I'm going to enter the backside. Okay? That's what happens. That's what a backside attack is. So all Sn2 reactions are backside attacks. Okay? Now, this does not apply to Sn1. There's no such thing as an Sn1 backside attack because, remember, in Sn1 reactions, we have a carbocation here. So the nucleophile has space to enter, right, and hit the carbocation without any interference from the leaving group because the leaving group has already left, right? The electrons associated with the leaving group have already left, right? They're already chilling here on the side. So the nucleophile has all the free range to come in at any angle and attack our compound, right? It can come in any angle and attack the compound, okay? So what this means is when you draw your mechanisms, you must always ensure that it's a backside attack. So the arrow is attacking the backside of where the halogen is, the alkyl halide is, okay? Okay, let's do some practice problems. Draw the mechanism and product of each reaction via Sn2. So we have R2 bromobutane reacting with hydroxide ion. So the first goal is actually drawing out what the molecule is. What's the starting compound? So how do we do this? Well, we're looking at this main molecule here. We have a butane, okay? So butane is 4 carbons long. Butane, or but, stands for 4. And this is saying it's 4 carbons long. So let's draw that in. Like that. Okay? 4 carbons long. We have a bromo here. Bromo stands for bromine. And it's located on carbon number 2. So we start from the left to right. 1, 2, 3, 4. This is number 2, right? 1, 2, 3, 4. We're looking at this carbon right here. And it's in the R configuration. So if you don't know what that is, please watch my other video on R and S configurations. But let me just draw this in. A bromine. All right? And it's going to react with the hydroxide ion. Our hydroxide is this. With 3 lone pairs. Actually, that's kind of ugly. Let me redraw it. I'm going to draw it with yellow. Okay. So, bromobutane reacting with hydroxide ions. So what do we do? Well, we're talking about an Sn2 reaction, right? So we are first going to do a nucleophilic attack. That's the first thing we do. And then we kick out the leaving group. That's what we always do for an Sn2 in that order. So let's draw it. So it's going to enter the backside. So these electrons here are going to enter the backside of the alkyl halide. And it's going to kick the bromine out like this, right? So remember, this wedge is a bond, right? And it has electrons onto it. So the bond is basically going to collapse and it's going to transfer the electrons onto the bromine so it can be free. So what do we get? Well, all we need to do is replace that bromine with the OH. But here is the thing. Okay. Notice that we have a wedge here. This means that this carbon is by default a chiral carbon. So if this was a wedge, we do a backside attack. Now this is going to be a dash now. It's going to be a dash now because it was chiral. So we must always flip-flop whatever it was. Now, remember, we kicked out the bromine and replace it with hydroxide. So we must complete the actual mechanism. You must draw in the bromine that we kicked out. If you do not draw this on an exam, you will get it wrong. Because if you don't draw this, it's basically saying, where did the bromine go? Right? It had to go somewhere. There we go. And that's how you do it. So once again, the hydroxide ion, rather the oxygen, the lone pairs on the oxygen, have attacked the backside of carbon number 2 and kicked out the bromine. The bromine is let free, and we replace the hydroxide ion. We substituted the bromine with the hydroxide ion, and we changed the wedge to a dash because the original carbon here is chiral. All right, that's letter A. Let's do B. S2 chloropentane reacted with NaSH. What do we do? Well, first we need to draw out 2-chloropentane. Pentane means 5 carbons, right? Pent, like pentagon, means 5 carbons. Chloro means chlorine, and the chlorine is associated with carbon number 2. So let's draw that in. 2, 3, 4, 5. Okay, and then this is an S, so it's going to be this, that. Okay, reacting with NaSH. Okay, so you may have not seen this before, but here's the trick. Whenever you see a sodium, ignore it. This is a trick, especially with Sn2. Ignore the sodium that's part of this, because that's not going to be doing the reacting part of it. It's the sulfur that's going to be reacting. So all we can just do is you can do this, sulfur and the hydrogen, and then draw in the electrons. That, and then this is a negative. Now you could draw in the sodium. So if I wanted to, I can draw in the sodium here, like this. But just know that the sodium is not reacting with the actual molecule, right? Because it's not a nucleophile. There's no electrons that's really associated with this sodium. It's the sulfur that has all the electrons. So this is what's going to act as the nucleophile. So when you do these mechanisms, you really only need to worry about what is reacting with what. Since the sodium is not reacting with anything, you don't really need to draw it in. But just for the sake of the example here, I'm showing you. All right, so let's draw it in. It's going to do a backside attack and attack the chlorine. That means this bond right here is going to transfer its electrons to chlorine and set it free. what we're left with is 2, 3, 4, 5. And then since this was on a dash, this means that this carbon right here is chiral because there are dashes and wedges. That means we have to switch it. So the sulfur and the hydrogen are going to take the place of the chlorine, and we're going to switch it to a wedge. Like that. And then we draw in the chlorine with its associated electron and a negative charge. Do not forget the negative charge. Because I have actually, during an exam, missed the negative charge when showing this mechanism and got points off for it. So make sure you don't do that either. So, there we go. And that's the mechanism for B. All right, let's do C. R2 bromohexane reacting with cyanide, sodium cyanide. So, we have a hexane. Hexane, like hexagon, means 6. So we're dealing with 6 carbon atoms. And there's a bromine because it has bromo in it. And the bromo or bromine is associated with carbon number 2. Let's draw it in. 2, 3, 4, 5, 6. And then this is R, so this is going to be on a wedge. Okay. Here is the question for you guys now. What's doing the reacting here? Is it the entire part of it? Is this entire compound? Is it just the sodium? Is it the carbon or the nitrogen? Well, here it is. Let me draw it in. There's a sodium. And then there is the cyanide part of it. And the cyanide is what's doing the reacting. The cyanide has 2 lone pairs. One lone pair. And you put the negative charge here. And then we draw it in. So this is going to react over here, carbon number 2, and we're going to kick out the leaving group, the bromine. Just like that, right? And then arrow. And then we just draw in the same thing, but replace the bromine with the cyanide and change the wedge to a dash. Because this is a chiral carbon right here. 2, 3, 4, 6. There we go. And then plus what we have left over, which is the bromine here, because we let it go. So make sure you draw in the electrons. 1, 2, 4, 5, 6, 7, 8. And then the negative charge associated. So there we go. So the trick is, whenever you see a reagent you're not familiar with, like this, that has sodium attached to it, don't worry about the sodium. It's not going to be doing anything. That's the trick. Only worry about the electronegative atoms. So this one is a little confusing, right? Cyanide. This is something you remember. It's the carbon right here that has the electrons that's doing the attacking, okay? That's the trick. All right, challenge problem. So, this compound, I don't know the name of, I don't know how to pronounce it, cameronanol or something like that, is a compound that has a woody fragrance. The derivative comes from an essential oil from plants. So a common technique in organic chemistry is to synthesize a compound artificially and then compare it to the structure to the naturally occurring compound. So this is how we make things, right, in the world. Is we don't really use the natural part of it, right? We use an artificial synthesis of it, but we need to make sure it looks exactly the same. So, this compound first undergoes deprotonation and then Sn2. Draw the mechanism. So, what do we do? This looks really confusing, right? Like, look at this huge molecule, right? It's nothing like this, right? But I promise you, it's exactly the same thing what we just did. It just looks complicated. Here's what we do. First, the answer is actually in the question about what we do. First, we have to do a deprotonation, and then we have to do an Sn2 nucleophilic attack. So, here's the trick. Only look at, don't worry about this at all, right? Don't worry about it right now. Look at the differences between this and this. What is different? Besides that it's yellow. The difference is right here. We have gotten rid of the hydrogen and replaced it with lone pairs. So that must be what's doing the reaction in this part right here. Okay? So, here's what's going to happen. We have to do a deprotonation. I went over deprotonation in the last video, so please check that out as well. But here's what we're going to do. So, this right here is potassium terbutoxide. The potassium does nothing. This is like a sodium. So whenever you see potassium, like this, for example, that is this right here. Potassium does nothing. For our instance, it does nothing. It's the nucleophile, basically a nucleophile in a way. The negative charge oxygen that does stuff. So here's what's going to happen. With a deprotonate, right? So the electrons from the oxygen are going to come over and steal the hydrogen away from the molecule. Okay? That means that this bond will collapse and turn into electron, which we're going to give right there. So this bond does no longer exist and will turn into electrons, which will be put right there, right? That is how we get this carbocation intermediate. Now, I said we have to do a nucleophilic attack, but you'll notice there's no reagents here, right? There's no OH or there's no sodium, right? Sulfide, none of that, right? No cyanide in here. So what do? This is what we call a ring close. This is very advanced, but I'm preparing you for when you see it. When a nucleophile attack can happen on its own self, on the compound itself. You'll notice that we do have a leaving group here. The bromine is a leaving group. So we're going to do the exact same thing that we've been doing. We're going to take these lone pair of electrons. Remember, it's just like everything else we've been doing, right? Lone pair, lone pair, lone pair. These lone pairs are going to go and attack the alkyl halide. Right here, right? Backside attack, just like normal. And they're going to kick out the bromine. Just like that. And when this happens, when a compound interacts with itself, it creates a ring. It closes the ring, right? So now we just kicked out the bromine and we can add it on to the side. We kicked it out. And then we add the negative charge. And there we go. We are now have the final compound, compound 2 right there. That is the challenge problem. See, it's not too bad, right? And maybe the hardest part was this part, right? But showing you that you can actually attack its own compound itself is very important. So if you ever see something with like no reagents here, that's what it's probably looking for. Now you're probably wondering, why is this not an Sn1? Right? We talked about a carbocation intermediate. Right? And it says carbocation. But why is this not a Sn1? The reason it's not an Sn1 is because this right here is a proton transfer. We are not doing a nucleophile attack here. This is actually a proton transfer. Okay, So the oxygen is stealing the proton away. That's what it is, right? We're not adding this group onto here, right? We're not doing that. That is why. So, if you found this video helpful, please like and subscribe. Until next time, later.